You know, every time you tap your phone to send money or book a flight or even just post a photo, you're placing your trust in a system. You just expect it to work. But what's really holding it all together? What keeps the whole digital world from just collapsing into chaos? Well, we're about to pull back the curtain on the invisible architecture, the unseen rules that make everything you do online possible. All right, so to kick things off, let's get right to the heart of the problem we're trying to solve. What happens when the very data we depend on breaks? I mean, just imagine this for a second. You go to send $100 to your friend. The money disappears from your account, but it never shows up in theirs. It's just gone into the digital ether. Now, this isn't just some scary thought. It's a very real technical problem that has to be solved. And that really is the core issue, right? A database, at its heart, is just a giant, dumb container for information. It doesn't know what's right or wrong. So without a really strict set of rules, even perfectly legitimate authorized changes could accidentally scramble the whole system, leaving you with data that's completely inconsistent and makes no sense. So, how do we fix this? How do we stop our money from disappearing into thin air? Well, the first part of the solution is this really powerful idea called a transaction. The key word here is atomic. Just like an atom was once thought to be this indivisible little particle, an atomic transaction is an indivisible operation. It's basically a promise. It says, either every single step in this process is going to finish successfully, or we're going to act like none of it ever happened. There's just no middle ground. Let's actually watch this play out. So our simple bank transfer, it really has two parts. Step one, debit the $100 from your savings. Okay, done. But then, bam, disaster strikes. A server crashes, the network connection drops, whatever it is. And that crucial second step, crediting the money to your checking account, it never even gets a chance to run. And this is where the magic happens. Because the whole thing was wrapped in an atomic transaction, the system sees that failure and immediately triggers what's called a rollback. It automatically undoes step one, putting that $100 right back where it started, in your savings account. It's like it never even happened. Your money never vanished. It's perfectly safe. So you can think of it like this. Every single transaction has one of two possible destinies. If everything goes off without a hitch, it's a commit. All the changes are locked in, they're made permanent. But if anything, and I mean anything, goes wrong, it's a rollback. The database is instantly reset to the exact state it was in before we started. No half measures allowed. Okay, so transactions stop operations from failing halfway through. But what stops us from putting just plain wrong or nonsensical data into the database to begin with? This is where our next set of rules, called integrity constraints, come into play. This quote really says it all perfectly. The best way to think about these constraints is like they're tireless little security guards for your data. They're on patrol 24/7. Checking every new piece of information to make absolutely sure it follows the rules and isn't going to cause any trouble down the line. And here are the three workhorses of data quality. The specific rules are guards in force. Not null is super simple. It just means you can't leave this field blank. Unique is the rule that prevents duplicates, so no two students can have the same ID number. And a check constraint is like a custom rule you make up, like making sure the semester field can only ever be fall, winter, or spring, and nothing else. Now we get to a slightly more advanced but absolutely critical rule, referential integrity. All this means is that the connections between different pieces of our data have to make sense. It's what stops you from creating, orphans data that's pointing to something that doesn't even exist anymore. And here's the perfect example of that. Let's say you try to add a new course and you assign it to the biology department. Well, the database is going to stop you right there if the biology department hasn't already been created in your main list of departments. It's enforcing that logical link, preventing that orphan data we were just talking about. And this is where things get really, really powerful. You can actually set up a rule that says, hey, if I ever delete the biology department, just go ahead and automatically delete all the courses that belong to it. It creates this helpful chain reaction, a cascade, that keeps all your data clean and consistent without you having to lift a finger. Okay, so our data is complete, it follows the rules, it's consistent, but who gets to see it and who gets to change it? That brings us to our final crucial pillar, authorization. Basically, who gets the keys to the kingdom? When you boil it all down, controlling access really comes down to these four fundamental permissions. Can you read the data? Can you insert new stuff? Are you allowed to update what's already in there?
And finally, do you have the power to delete it? Pretty much every security system you can think of is built on these 4 simple actions.
Now, you can imagine that trying to hand out these permissions one by one to every single person would be a total nightmare, and that's exactly why we use roles. A role is just a way to bundle a whole set of privileges together under one convenient name. The analogy here is perfect. It's way easier to give someone the single manager key than to hand them a giant, clanking keyring with 20 different keys on it. A university is a great way to picture this. A student role might only have permission to read the course catalog. An instructor role can do that, plus they can read student lists and update grades. And then a dean role has even wider access to manage entire departments and faculty. Each role gets exactly the permissions it needs and nothing more. And the system gets even more clever. Roles can actually be granted to other roles, which lets you build this really efficient hierarchy. So a dean automatically gets all the permissions an instructor has, plus a bunch of their own extra administrative powers on top. It makes managing security for a huge, complex organization so much simpler. So let's step back and bring this all together. We've basically looked at 3 huge potential problems and the 3 powerful solutions that create the rock-solid foundation for any system you can really rely on. And here they are, the 3 pillars of data trust. You've got transactions, making sure our operations are always all or nothing. You've got integrity constraints, making sure the data itself is valid and follows the rules. And you've got authorization, making sure only the right people can get their hands on it. And that's really the big idea here. It's these 3 things working together silently in the background that transform what would otherwise be just a chaotic bucket of information into the reliable, consistent, and secure systems that we depend on for, well, pretty much everything in our digital lives. So, I'll leave you with a final thought. Every single app on your phone that you trust with your personal data is built on these 3 pillars. But if you had to pick one, just one, as the most critical, the absolute bedrock of that trust, which would it be? The all-or-nothing promise of transactions, the strict rule-following of integrity, or the lockdown security of authorization? Something to think about.